So hello everybody, now is the second talk of this session by Professor Richard James from the University of Minnesota. So please, Professor, start.
So thank you very much. So it's a great honor for me to be here, especially in view of the fact that I actually sit in the engineering department, but I make a big effort of moving out and not only interacting, but really trying to learn in a deep way some other fields. So I hesitated when I was asked to give a title for this talk because of the fact that I work in several areas, and this would be the natural area for me to give a lecture, but I won't give a lecture on that subject, but there is a reference if you want to see something about the relation between mathematical theory and the discovery of materials. What I will speak, and the reason that I chose this topic was that on reflection, I recalled that Brazil was a world center for dynamical systems. So I do have a part of my work which is related to that area, so that's what I'll speak about. And it's an invariant manifold of the equations of molecular dynamics. So there are two threads which run through my talk. One is the time scale limit of molecular dynamics, and this is a very fundamental, very pervasive. It's a major bottleneck in physics, engineering, biology, in all of the sciences. Everybody would like to compute molecular dynamics for long periods of time, but this is the current state of the art, is that with reasonable atomic forces, it's hundreds of atoms for only nanoseconds. And that does not answer most of the questions that people have about dynamical behavior of materials. And the second is non-equilibrium. This is an old big problem, is non-equilibrium statistical mechanics. And it's the question of whether we can have a non-equilibrium statistical mechanics that's built somehow from molecular dynamics, from a real dynamics, let's say, and that has the simplicity and generality of equilibrium statistical mechanics. In general, I think that's not true. But what I'm going to offer is, in a special case, something that can't be considered a final solution, but a suggestion for both of these things. So here goes. My talk is built on the use of isometry groups. So let me tell you about isometry groups. They're consist of orthogonal transformations, say in 3 dimensions, and translations. They can act on points in R3 in that very classic way. If you have two isometries, G1 and G2, the multiplication rule is this multiplication rule. And that rule comes from the composition of mappings. So G1 times G2 of X, where this notation is explained here, is G1 of G2 of X, using the same notation. There's the identity. And the international tables of crystallography are the repository for the isometry groups. So if you're not very familiar with this multiplication rule, I'm going to be taking a lot of orbits of groups in different ways. Let me illustrate it. Here. But in a slightly different case, I'm going to illustrate in the case where it's the so-called conformal Euclidean groups. I'm going to add a real number there, and then it still can these conformal transformations still can act on points in R3 by the rule you see right there. The product rule is still composition of mappings. So if you want to get a kind of illustration of this, you can work out the conformal transformations which commute, and then you can take powers of those to form a group. And if you take that group and you act on that little square, you get the symbol for the ICM Congress. So that's the type of thing I'm going to be doing a lot, is taking action of group on these kind of groups, particularly the isometry groups on on some special points. In my talk, I'll use two kinds of isometry groups. The translation group, that's the easy case. It's the powers of 3 translations, which I gave earlier. So it's just like this, with P, Q, and R with integers. I'm going to also use the so-called helical groups late in my talk. Hopefully I'll get to that. And that's governed by this theorem. And actually, the helical groups are not in the international tables of crystallography because the organization scheme of the international tables, which was based on the solution of Hilbert's 17th problem, does not allow. There would be infinitely many groups if they included them according to the scheme of the organization of the international tables. It's a bit of problem for people in applied mathematics, I would say. Anyway, I'm going to use the groups that are based on this theorem. If you have a discrete group of isometries that does not contain a translation and does not fix a point, it's expressible in one of these forms. And there's some pictures, and everything's explicit. You don't have to read it. But the point is, everything is explicit with its parameters displayed here. And the point is, to understand this, what I did was I took this blue ball here, and I took the orbit of this blue ball under this group. So I get this picture, so you can kind of understand what this group does. And this is the case B, and I took, again, the orbit of a single ball under this group. In fact, I colored the balls according to the power of m, and so forth and so on. So you can see a bit how those helical groups look. Okay, so now I'm going to describe a time-dependent invariant manifold of the equations of molecular dynamics, and it's the main subject of my talk, and it goes like this. So I'm going to describe it not first as an invariant manifold, I'll tell you about that later, but first I'll describe it as a numerical method. So we're going to have some atomic positions in 3 dimensions, and these are denoted yk of t. And k goes from 1 to m, and those are the so-called simulated atoms. Those are the ones we're actually going to simulate in the numerical method. And then there's going to be other atoms, the non-simulated atoms. They're given by the group. So I take one of these isometry groups, and I act in the way I just described. I take the orbit at every time on the simulated atoms. And I get other atoms. And so it's natural to use this index notation with I and k. I goes from 1 to n. Usually those groups, all the groups I just described are infinite, so usually n is infinite. And k goes from 1 to m, that's the index for the simulated atom. So you get copies, in a sense, of the simulated atoms by this formula. And now I'm going to do something else. So if you recall from the last slide, we had many parameters in those isometry groups. I could allow those parameters to depend on time, okay? I'm going to do that, okay? So there's going to be time dependence. So it's an additional explicit time dependence besides the time dependence in yk. But the time dependence is going to be very restricted, and it's going to be such the second time derivative of this non-simulated atom is given by q times the second time derivative of the simulated atom, where the group element is qc. Okay, qjc straight. Okay, so obviously that's quite a strong restriction on the group, on the time dependence of the group, as well as on the motion. And I'll come back to that in a minute and tell you exactly what it means. But just say there's a time-dependent restriction on time dependence. Okay, so that's what it is. Okay, now I'm going to tell you about the atomic forces. I'm going to solve Newton's laws of motion for all the atoms. And there's standard, and I'm going to use the invariance of the atomic forces. So I'm going to be, the standard invariances for the atomic forces are, first of all, frame indifference for Q in O3 and C in R3. Then this holds. And my notation for the atomic forces, I guess, is shown there at the top. that's the force. I use this suggestive notation for the force on atom I, k. And it's very simple. You just take the Q, you take any isometry, you take the Q, and you can bring it inside, and you can add the C. That's a condition that's satisfied by all accepted models of atomic forces. And I'm also going to assume permutation invariance. Permutation invariance is this condition. It's also very simple. It says that if you put a permutation, if you on two indices of in this place, then you can bring the permutation inside. And that's a permutation which has to preserve the species of the atoms, as you might imagine. So those are the standard invariances of quantum mechanics, and I'll use those. It's the main tool I'm going to use. Okay, so here's the theorem. Okay, to just one more remark about those invariances. If you had a potential energy, and it was permutation invariant, and it was frame indifferent, and you differentiated this, you would get the conditions on the previous slide. So it's very, very standard. Of course, in many cases, n is infinity, so I usually don't even, though I sit in an engineering department, I don't differentiate infinity. Okay, so here's the main theorem. It's very simple, actually. So it assume these invariances I just said, and let this G be a time-dependent. Recall, I allowed those parameters in the group to depend on time in a particular way, but they had to satisfy some restriction. I'll tell you about that in a second. And let these yk, in other words, the simulated atoms, let them satisfy the equations of molecular dynamics. So, of course, on the right-hand side are all the other atoms. Because, of course, the force on a simulated atom comes from all the atoms. So this depends on all the atoms. But, of course, the non-simulated atoms are given by group transformations on the simulated atoms. And there's an explicit dependence on time in here that I left out to make it readable. So once you see that the right-hand side is actually only dependent on the positions of the simulated atoms. So these are a system of m ordinary differential equations in standard form. You put initial conditions of the standard type, and you compute a solution of this. And the theorem says that the non-simulated atoms also exactly satisfy the equations of molecular dynamics for their forces. Okay? So that's the theorem. I mean, there's an easy analysis part of this proof, which is dealing with the infinite number of atomic positions. But the heart of the proof is simply a calculation. It's here. It's the fact that I assume that the simulated atoms satisfy molecular dynamics, and now I simply compute the m times the second derivative of a non-simulated atom. I use both the permutation invariance and the frame indifference, and I see that they satisfy the equations of molecular dynamics. So this in fact is, I promised I would come back to this. I'm allowing the group elements to depend on time, and I never told you, subject to some restriction, which I'm going to do right now, and I'll tell you what that is. So here's a group element, and in general, Qj depends on time, and Cj depends on time. Same notation as the first slide. That's a group element in an isometry group. Of course, I can introduce the skew matrix W, which satisfies this. And that's the condition I wrote on the slide, which is about the time dependence. And so you just differentiate and you work out this condition, and it's that. And you see it's very restrictive, as expected. You know, and how am I going to satisfy these? These are the simulated atoms. I know virtually nothing about the motions of those simulated atoms. I can't satisfy this equation in a statistical sense. I have to satisfy it pointwise. So the only way to satisfy this condition without some huge restriction on the motion is that C double dot is 0 and W is 0. And so C is A, T plus B, and Q is constant, okay? And you might think, why did I waste my time doing this? Because it just looks like a Galilean transformation. But in fact, because this can depend on J, and this can depend on J, there's actually quite a few different time dependencies that are possible. Of course, you still have to worry about whether it forms a group when you introduce this time dependence. So that's the situation. Okay. Now, you can rephrase this as an invariant manifold of molecular dynamics instead of a numerical method. And here it is. So here's the momenta, and there's the positions. Of course, typically n is infinite, so there's infinitely many axes over here. But anyway, that's the way it is. And there's the formula for the momenta, and you can see for the non-simulated atoms, and you can see that these formulas mix up the formulas for the simulated and non-simulated atoms, and there's an affine time dependence. So what is that? That's a manifold in PQT space. So there's an invariant manifold corresponding. This method of simulation is on an invariant manifold. And these invariant manifolds, there's in fact lots and lots of them. And because there's lots and lots of isometry groups, and there's lots and lots of time dependencies. So this is a very much unstudied invariant manifold of general molecular dynamics. And I'd like to tell you about it. Another thing about it is that, look at these formulas. There's no atomic forces in these formulas. There's nothing about the material in these formulas. This means that this manifold is independent of the material. If you're simulating steel, or you're simulating water, or you're simulating air, it's exactly the same invariant manifold. You can write those invariant manifolds ahead of time. Mostly they're unstudied, and I think they're quite interesting. So I propose to try to learn something about this invariant manifold. Okay, let's explore this a little bit. Let's take the translation group. That's the simplest case. And of course, the time-dependent case is really the interesting case. So suppose that I'm allowed, in this case, what's the time dependence I'm allowed, consistent with what I said earlier? I'm allowed to make these three vectors, E1, E2, E3, affine in time, okay? And so these are translations, and the translations are parameterized by 3 integers, so it's natural to use this notation y and some nu and t, and nu is a triple of integers, and k is the index for the simulated atoms. So this is the notation for the non-simulated atoms, so all the atoms if you want. And the simulated atoms would be the case where you take nu 0, 0, 0. And this says that the non-simulated atoms are given by the simulated atoms by using the group. So it's just yk of t plus nu I ei hat. Ei hat can be affine in t. I'm going to write that in a certain way. I'm going to write it as identity plus t times the 3 by 3 matrix A. And these are any 3 linearly independent vectors. So, and that's a general way to write affine time dependence. And it's this 3 by 3 matrix A is going to play a huge role in this talk. Okay, that's what you get to choose for the translation group when you're doing one of these simulations or the invariant manifold viewpoint as well. Okay, so how do you do this simulation? So you take any number of atoms. These are going to be the simulated atoms. You put them anywhere, and you give them any initial conditions. Okay. Now you take 3 linearly independent vectors. So I just take 2 there, but imagine with my fingers 3 linearly independent vectors, and I extend those atoms periodically. Okay, so there we go, at t equals 0. And now I just simulate the simulated atoms. And these 3 vectors change affinely in time. They're allowed to they're changing affinely in time according to the matrix A that I just talked about. And at every time step, I extend the simulated atoms by that periodicity. And the theorem says that all the atoms satisfy molecular dynamics. Okay, so you may, okay, let me first, before I show you a simulation so you get an idea what it looks like, what is it's a translation group, so the atoms fill all of space. And there's some kind of, because I have this time dependence, there must be some kind of macroscopic motion. What is the macroscopic motion of this simulation? So that's easy to figure out. But it requires an additional assumption on the atomic forces that I'm just writing in words here. I hope it's understandable. It says if you take any configuration, any time, for example, and you compute the force on a collection of n-cubed unit cells that look like this, and divide by n cubed, all the models of atomic forces have the property, all the classical models certainly have the property that this goes to 0 as n goes to infinity. But I write it down because it's not all models, because in the Coulomb case, this would be a very delicate thing. You would have to have charge neutrality, you would have to very carefully study screening and so forth. So Coulomb is the borderline case. But all the usual models that people would take, this is satisfied. Okay, so if you have that condition, you can prove the center of mass of the simulated atom moves with constant velocity. And let's assume, using an overall Galilean transformation, that's 0, which you can do. And then the centers of masses of the images of the like these points here, of the images of the center of mass of the simulated atoms move on a grid according to the following motion. This works better if I do this sometimes, anyway. And so it's very simple motion. So that's the overall motion that's the macroscopic motion of this simulation. Okay, very good. Now, okay, I'll show you an example of one of these simulations, but I have to set the stage because it's hard to show an example of a simulation in which the atoms fill all of space. So, first of all, I'm going to do the most simple case. It's simple shearing. That corresponds to a choice of that 3 by 3 matrix A, which is rank 1 and trace free. Okay, that's simple shearing. And I'm going to color the simulated atoms blue, and I'm going to show where they go. So you'll see all the simulated atoms for all the time of the simulation. But the non-simulated atoms would cover up the simulated atoms. So for the non-simulated atoms, I'm going to make a box, and the box is going to be deforming according to this changing periodicity. Okay? And I'm just going to show, it's actually a 3-dimensional slab, and I'm just going to show the non-simulated atoms in red in the slab. Okay? So in short, simulated atoms are blue, non-simulated atoms are red. Okay, so there's a typical simulation. So every atom, I mean, of course, out to infinity, is satisfying molecular dynamics. I'm only simulating the blue atoms. And what I like about this, fit is so you're seeing, the reason it switched is because it reached the edge of a frame, and then I redefined the periodicity, and I continued. But I was using it's effectively the same periodicity, just use the ideas from crystallography. So you can see that what's interesting is the simulated atoms diffuse into the non-simulated atoms, of course, and there's a lot of interesting dynamics going along here, but it's not related to the Gibbs distribution. This is not the equilibrium case. Okay, of course, there's very interesting things with there's choices of A where you have dilatation. There's choices of A where you have vorticity. You can have vortex stretching. There are many interesting cases you can look at. You can have the temperature go to infinity in finite time. You can have many interesting things. So now I want to discuss how does this simulation relate to continuum mechanics? So there's the motion I Lagrangian form of the motion. I'm going to look at fluid mechanics, so you just calculate from this the Eulerian velocity field that's given by this expression. And let's take, for example, the Navier-Stokes equations. Suppose I substitute that formula into the Navier-Stokes equations. Sigma is the stress, and sigma is affine in the velocity gradient, the Eulerian velocity gradient. And the point is, it's identically satisfied. That's because for this function v, its velocity gradient is only a function of time, so the divergence of the stress is 0, and the left-hand side is 0 because of this calculation. Okay? So that's Navier-Stokes. Of course, it's true with Euler, but it's also true if you take some, exotic theory of non-Newtonian fluid mechanics. It's still true. In fact, all the accepted models of fluid mechanics have this solution. Okay? Even models of liquid crystals have appropriately, you have to take into account the director, but they have this solution. Okay, now, you could also include an energy equation, and so all of mass, momentum, and energy you could include. And then in the continuum mechanics case, the temperature would become a function of time only, and the energy equation would become an ODE. And it would not be material independent. That would depend, the evolution of temperature would depend on the material. In the simulation, in the molecular dynamics simulation, you can argue that the temperature should be the mean kinetic energy of the simulated atoms after you subtract off the macroscopic velocity. And you see that that is independent of which copy of the simulated atoms you use. And so that's the natural thing to compare with this theta of t. Okay, now let's go to a theory which is intermediate between molecular dynamics and continuum mechanics, the Boltzmann equation. So what does the Boltzmann equation, how do we understand this molecular dynamics simulation at the level of the Boltzmann, or can we understand it at the level of the Boltzmann equation? So as you could see already, even in the last talk, it was effectively a Boltzmann type theory was discussed. So it's the unknown is the molecular density function, the probability density of finding the velocity v in a small neighborhood of y at time t. The probability density is in the velocities. And it satisfies this equation, of course, very famous equation, very much talked about in this Congress. I won't tell you all the details, but just to explain the notation, this star primes and so forth just indicates where these molecular density functions are evaluated. There's the physics comes in this function. It's in the form of that function comes by solving the two-body problem of molecular dynamics. Very simple problem to solve analytically. You solve that problem, you get some angle omega that comes out of this solution. And this is used to build the function b. And b is completely explicit. So crash course on Boltzmann equation if you don't know it. Okay, so how does this, okay, so think about one of these molecular dynamics simulations now. And I'm going to, so you're in the middle of one of these simulations, and I'm going to make a ball about, in fact, any point of any radius, okay? And now I'm going to look at the velocities in that ball. And at this particular time, there's some periodicity. So, and now I'll take another ball of exactly the same radius, and I'll put it periodically related to the original one. And it doesn't actually have to be at 0. It could be anywhere, but anyway, I'd put it at 0. Okay, and the point is that if you think about it, in this ball are some simulated atoms and some non-simulated atoms, maybe. And in this ball are some simulated atoms and some non-simulated atoms. If I know the velocities in this ball, I automatically know the velocities in this ball. Okay? And that comes from the simulation. And so the method of simulation, and you can say it this way in words, that the velocities sort of at 0 are yi dot. The velocities here are given by yi dot plus ax. The Boltzmann equation is an Eulerian theory, so it means that the velocities, should say, the velocities at y are the velocities here plus a identity plus ta minus 1 times y. That's just convert to Eulerian form. So, but the molecular density function of the kinetic theory of the Boltzmann equation is supposed to tell you the probability density of finding a velocity v in these small balls. So it immediately tells you an ansatz for the molecular density function. It's that. And now that's not written as an ansatz. There's the ansatz. It says that the molecular density function for corresponding to simulation should satisfy this requirement, which is a big reduction from 7 variables to 4 variables. Okay, you shove that into the Boltzmann equation and it exactly reduces. So even though Boltzmann equation is time irreversible and molecular dynamics is time reversible, again, Boltzmann exactly inherits this invariant manifold. It's in a way remarkable. This equation, I think, wasn't written down until we did, but many people have studied the equations of the moments of this equation. People study that independently of the Boltzmann equation. Even Maxwell wrote down the equation for the moments. And Sergignani in particular studied the case in which this reduces to a constant and in fact gave an existence theorem for this equation. So another thing that's interesting is the periodicity has disappeared. So, but in the most faithful possible way, this inherits this invariant manifold. Okay. So of course everything could fall apart like a house of cards if you don't have an existence theorem. And recently, with help from especially Alessia Nota at the University of Bonn and Juan Velasquez, we gave an existence theorem for this equation. It's for positive solutions actually in measures, and it's a concept of mild solution. And there's also a uniqueness theorem as well. There's a unique mild solution to this reduced equation. And it's in the case of assumptions on B which effectively reduce it to so-called inverse fifth power molecules, which I'll tell you about in a minute. Okay, first of all, before I tell you about that, in the Boltzmann equation, or the kinetic theory of gases, there are formulas in terms of the moments of the molecular density function of macroscopic quantities: density, velocity, energy or temperature, stress, pressure, heat flux. So just so you see, and there's a theorem that says for good enough solutions, the balance of mass, momentum, and energy of continuum mechanics is satisfied. If you calculate these for this ansatz, for the invariant solutions, they come out what you expect. The density is given by a formula. The velocity is given by exactly the formula I had for continuum mechanics plus Galilean transformation. And these become functions of time alone. Okay. The most interesting thing is the H theorem, because that's the theorem about the entropy, which is minus the H function. And if you calculate, and it's given by this famous formula, it's given by this famous formula, which under the ansatz becomes just g log g. And it's the fact that H is decreasing is the H theorem for these invariant solutions. Now I want to make a remark which seems unrelated, but I'm going to come back to it in a second. There's something called the Maxwellian density. That's this density. And it's the density which corresponds to equilibrium. It solves the Maxwell-Boltzmann equation because it makes the collisions operator on the right-hand side 0. And here I've written it in terms of these moments, in terms of the energy or temperature, and also here, and density is here. So it can be written in terms of its first few moments, like this. And the value of H for Maxwellian densities is this, minus log temperature to the 3/2 of a rho. E is energy, but it could also be interpreted as temperature. Minus log temperature to the 3/2 of a rho plus constant. So that's something about equilibrium in the Boltzmann equation. It has nothing to do with our previous discussion because we were far from equilibrium. But I need to tell you about it. Okay, now we're going to go to inverse fifth power molecules. So I picked a little thing out of Maxwell's first paper on the kinetic theory, and he talks about his assumptions in the days before molecules were totally understood. But he made this modification because of the fact that in his experiments, Maxwell did experiments too, on the viscosity of air at different temperatures. He deduced from these experiments that the repulsion, that goes into that B, the force law goes into that B, and the repulsion is inversely as the fifth power of the distance, so-called inverse fifth power molecules. I always thought this quote was Maxwell being tricked by mathematical simplicity. Perfect. Because on inverse fifth power molecules, people well know that there's an extra invariance of the Boltzmann equation. It satisfies this very particularly good invariance, the collisions operator. But in fact, I actually learned from Gerhard Frieseke, a mathematician in Munich, that this inverse fifth power of the distance is a very reasonable force law for 2 nitrogen molecules. So actually, the experimental part of this thing is meaningful as well. It's quite a tribute to Maxwell to come up with that. Okay, so you can further simplify this equation, the reduced Maxwell-Boltzmann equation for inverse fifth power molecules. And in fact, you can solve it by scaling. So you can do this. And I'll tell you about the cases for simple shearing and planar shearing. Those are really the only cases we can really do. So there's simple shearing. That corresponds to the case I showed the simulation earlier. It looks like that. And the macroscopic quantities here, the density is constant, the velocity. So I'm telling you about the moments of the solution of the reduced equation. There's the stress, the temperature. This beta is negative. The temperature is going to plus infinity exponentially. So it's really a far from equilibrium flow. And you can calculate explicitly the H function. So there's the H function. So again, far from equilibrium because the H is going linearly to minus infinity. But if you compute the H, and you notice that it's given by minus log e to the, even though the temperature is going exponentially to infinity, H satisfies minus log e to the 3/2 of a rho plus constant. But that's exactly the same law as in the equilibrium case. So even though there's no we're far from equilibrium, there's no Gibbs distribution here, there's no Maxwellian, it's the same relation between entropy, density, and temperature is satisfied for the invariant solutions. That's, to me, a remarkable accident. But there's one difference. The constant is different. The constant is different from the equilibrium case. It's strictly less. So there's many, many interesting things to discover here. Planar shearing is even more interesting. Because there's the macroscopic motion. You can think of this as, although there's no plates in the simulation or the Boltzmann equation, you can think of it as 2 plates coming together or going apart and the flow between them. There's no boundaries, of course. All the solutions are on all of space. There's the macroscopic density and temperature and stress and so forth. There's the H function. This one is even more non-equilibrium. This H goes to minus infinity infinite time, at least with the right signs. But again, even though the density, H, the temperature, and rho are changing, you have exactly the same relation between H, density, and E. But there's a constant, and the constant's different, once again. So these are very interesting to me coincidences about relationships which are thought to only hold in equilibrium, but they're holding in a highly non-equilibrium situation. Okay. You know, so the dream here would be, of course, that there's a probability measure, which is not the Gibbs distribution, on the invariant manifold I've been discussing, depending on A and the atomic forces, and maybe macroscopic properties are given by its moments. It turns out that we think that's not true. We find that there are different behaviors depending on the choice of A and depending on the atomic forces for these inverse p-th power molecules. And in some cases, the hyperbolic terms in the Boltzmann equation dominate. In other cases, the collisions operator dominates, and we do get some different behavior. So I think it's not as simple as equilibrium statistical mechanics, but I believe there's a statistical mechanics on this manifold. Okay. Now, I'm finished my talk. I think I have maybe 4 minutes or 3 minutes. You know, I claim that you could use any isometry group. So why don't we use a helical group? So I'm going to use this group C. It's right there. And so again, the scheme is the same. I have some simulated atoms. I use the group. I take the group orbit of those simulated atoms to get the non-simulated atoms. I solve molecular dynamics for just the simulated atoms. All the atoms satisfy molecular dynamics. Same scheme. And so the question is, where can I put the time dependence? So here's the group, and here's the generators. So there's some parameters, and I'm allowed to put the time dependence consistent with what I said in right there. So I'm allowed to make that tau affine in time, and I'm going to make it affine in this way. So, and what I'm going to do is, so that's a helical, some kind of helical structure. So I'll choose the initial positions, and I'll choose the atomic forces consistent with those of carbon. So I'm going to do carbon nanotubes, okay? And these are typical choices, say initial choices of simulated atoms, either a helical set of simulated atoms or something like this. We did many cases. And here's a typical simulation. So I have to show you here. Put my finger right here. So you can see that it's getting longer. So this is, I'm pulling the carbon nanotube at infinity, and it's extending. Of course, the atoms are feeling only the forces of the other atoms. There's no artificial forces that are stretching this. The forces, you might say, are at infinity. And then eventually, it fails. And the whole story about failure is also very interesting, but I'm not going to tell that story. I'm going to tell a little story in maybe 2 minutes about again, accidents, like I showed with the Boltzmann equation, accidental relations. So here's typical temperature versus time from a simulation like I just showed you. So actually, the carbon nanotube, as you stretch it, it cools. That shows that these forces are at least accurate enough to show you that this cooling shows you that a carbon nanotube acts more like a metal than it does like a polymer. And then, of course, at some point it fails, and that's seen by a great increase of temperature. But here's a remarkable thing. If you do many simulations, and you start at many different initial temperatures, and you, instead of plotting temperature versus time, you plot temperature versus strain, which are both changing in time, then you get this remarkable collapse here. And you get collapse even though you're changing the strain rate 2 orders of magnitude here. Of course, when you start to fail, everything changes. But there's an amazing region of a relationship between temperature and strain, which you certainly wouldn't expect it far from equilibrium. Here's an even more remarkable one. This is over 4 orders of magnitude change in the strain rate, and this is temperature versus strain again, and you can see this this amazing agreement. This is force. There's a way to calculate the pulling force from the atomic forces in this simulation, and accepted way. And this is, again, the force up to the point of simulation. Even though the rate is differing by 4 orders of magnitude, there's some special relation. Okay, so this brings me to my summary, which is this. So, as I said, there's lots and lots of isometry groups. Even the translation case is not studied, hardly studied. And there's a family of time-dependent invariant manifolds of the equations of molecular dynamics. And it's independent of the material, and it's true in all cases. No restrictions on the atomic forces. I mean, you have to have molecular dynamics, that's all. This manifolds can describe far from equilibrium behavior, and it seems that simulations can reach realistic time scales for macroscopic motion, so it provides some method of reaching macroscopic time scales. There are many open mathematical questions here. One of the most difficult one is there are no rigorous results on how many simulated atoms you need to get kind of repeatable behavior as you would increase the number of simulated atoms. That would be a typical thing one would do. For the translation group, you have the freedom of choosing any 3×3 matrix A, and macroscopic velocity fields are always given by that formula. Includes lots of things, as I mentioned. The Boltzmann equation and all of continuum mechanics inherits these manifolds in the most straightforward way, despite the fact that Boltzmann and continuum mechanics are usually time irreversible, whereas molecular dynamics is time reversible. So that's a remarkable, to me, that's a remarkable fact. Okay, so the big news is I think that it would be a big step forward, comparable to the discovery of equilibrium statistical mechanics, which was used many times in this Congress, to be able to write a statistics on this manifold. And as I said, studies of the Boltzmann equation, which give you insight into one view of this manifold. Of course, the molecular dynamics view is much more general because it includes many more kinds of materials, indicate that this may be possible, but it's not as simple as there's a probability distribution on this manifold, and you take its moments to calculate macroscopic properties like equilibrium statistical mechanics. So, thank you very much.
Okay, any question? Please. Okay. Yes.
Yeah.
Thank you for your presentation. Is it possible to explain what kind of numerical method you use for some of your simulations?
Yeah, so we use the velocity-Verlet algorithm, which is a very famous algorithm for molecular dynamics, to do the molecular dynamics simulation. And actually, an interesting thing about the velocity-Verlet algorithm is even on the discrete level, it inherits the same invariant manifold. And I think even true with, I would have to check this, but I think it's even true with integer arithmetic. So it's a very good, this invariant manifold is a very good match for velocity-Verlet, which happens to be a very good method for studying molecular dynamics. But I haven't looked beyond, I mean, we use that method in the simulations, and I haven't looked beyond that in the numerical case. Of course, there's also numerics for Boltzmann, numerics for continuum mechanics too, and that's all, I have no remarks about that, but should be interesting to try to do it there as well. Yeah.
Because it was my question, if you use a supercomputer, make some of your simulation, or if it's just a normal computer?
We have used both. The simulation that I showed you, the first one, was done on it's done on a supercomputer, but one processor, so it's a small machine. Yeah. So to reach realistic timescales, one has to be very good about finding neighbors, because you have to calculate the force on a simulated atom. So the efficiency comes all in finding neighbors, in resetting the periodicity at certain times, and also the parallelization and so forth is completely open. And I'm really not expert about that, but so it's largely an open question. Yeah. Yeah.
Other questions?
Your simulation there, the failure simulation for the nanotube, suggests that a certain minimum number of atoms is required to even see that. Or reversely, that certain phenomena cannot occur. If the numbers, can you comment on that?
Yeah, I can. Because that was our main concern, actually, and we wrote some papers about that. I can give you more references, but and we only did empirical things. So we systematically increased the number of simulated atoms. Of course, in molecular dynamics, you always have to prepare the initial data. So in all the simulations, otherwise you get garbage, or you get a long period of nonsense, and then you start. But so with prepared initial data, if we would measure, so here's the things we would measure. We would measure the initial temperature of the simulation. That's mean kinetic energy of the initial data. And the strain rate is given as a parameter of the group. So two parameters, temperature, initial temperature and strain rate. The failure strain was incredibly reproducible as a function of initial temperature and strain rate, as long as we had about, say, 50 or 100 simulated atoms. Something on that order would give us amazing reproducibility of the failure strain. So that's a very important thing to calculate. That's what we mainly wanted to calculate. And the failure strain varied from about 25% strain to 1% strain, depending on the initial temperature and strain rate. And some of this was quite unexpected. But if you graph the failure strain as a function of initial temperature and strain rate, you get a very reproducible surface with about 50 simulated atoms. So that's the empirical observation, yeah.
Great. Other questions? Okay. So we thank the speaker again. Thank you.